We've been talking about artificial intelligence explanations of question answering. How can a computer explain why it answers a question in a particular way? Throughout our conversation, I've been complaining that the plethora of explanations we've seen don't actually test whether the explanations are useful to a human. The explanations that we have seen have been at the bottom of this hierarchy. One of the first two levels. Can we get an application-grounded evaluation of question answering? But what would be the application? I want to talk about two applications, question answering and crafting adversarial examples. Wait, I hear you ask, how is question answering an application-grounded evaluation? Haven't we been seeing systems doing question answering throughout the whole semester? I hear you ask. Aha, but I'm not talking about a computer doing question answering. I'm talking about a human-computer team doing question answering. And in this setting, we transfer the accountability from the machine to the human. We want to measure the application of a human answering questions with computer support. This happens by the computer sharing its prediction and then seeing how that affects human performance. Recall how we talked about interpretations only matter when there's something relevant to say. If the human or computer dominated the other, this wouldn't be worth it. But as we saw in crosswords, humans and computers have different skills and strengths. But how does a human know when to trust the crazy stuff the computer is saying? That's where explanations come in. We keep the underlying model fixed, but vary the explanations that the computer spits out. The computer can show what it's thinking, the weight of the guess, the evidence that it's using, or what parts of the input causes it to think that this is the answer. Now, you might think that answering questions on a computer is weird and that only crazy people would do this. You're right, but there are plenty of crazy people out there. About a decade ago, we created a web page so that people could play Quiz Bowl, the quiz sport of kings, online. Words appeared one at a time, and people answered when they could. Now, we collected all the data we needed and shut down the site after about 2 weeks. But people liked it so much that bootleg versions started popping up, the most popular of which was Proto Bowl. Here's Ryan Letourneau streaming themselves playing Proto Bowl online.
Established that software was not afforded the same protections as literature. These programs lend their name to a program once hosted by Leo. I buzz in! Screensavers.
If you take a look at our interface, it's pretty similar. We just replaced all of the social components with machine learning, as it should be. In the upper left, we see all of the top guesses from the system. The bottom middle has the evidence the system is using. And the highlighting shows the most important words that the model is using to retrieve the evidence. And the highlighting is in both the question and in the evidence. As usual, the question reveals itself word by word, and people can give the answer when they know it. Each of these three components can be either on or off, so that's a total of 8 different experimental conditions. We ran a linear regression to see how much each of these components improves the score of the human-computer team. If the coefficient of the interpretation is positive, it helped. The bigger it is, the more it helped. And all of them help. That's great. But remember how I said that application-driven evaluations depend on the people who are interacting with the system? Well, now we have evidence to support that. We had 2 pools of users, novices, random people on the internet, and we have experts who have experience playing Proto Bowl and know a lot of trivia. It goes without saying that the experts are overall much better. They had much overall quicker reaction times and higher accuracy. But for our purposes, we're just looking at the improvement, the relative improvement over their baseline for the 2 groups. If you look at the coefficients, the novices need the evidence. They need to look at Wikipedia to figure out what the answer is. On the other hand, the experts benefit a lot more from highlighting. This either helps them see what's important quickly, or to double check whether the computer's logic is on track. Okay, those are each of the interpretations in isolation. Let's think about interactions. When we have multiple features on, we also have an interaction feature. If the interaction feature is positive, there's a synergistic effect. Together, they're better than either on their own. That's a cyan. But if it's negative, like the red arrows, what does that mean? Our best guess is that when the interaction is 0 or negative, then the user is getting overloaded. There's just too much going on and they can't see how it all fits together. The experts seem to do better with more information. Maybe that's not surprising. Now, there's plenty to criticize here. We could have designed the look of the interaction better. Relevant things could have been closer together, what have you. And we could have done all the fancy explanations that I talked about in the previous video. We mostly didn't do that because it was all happening contemporaneously. But despite all of these many faults, it's a recipe that you and your friends can and should use to validate how useful your interpretations are. And it's fun, too. To wax a little philosophical for a moment, this is the direction that more of our research should be going in. Investigating human-computer teams and measuring how effective those teams are as collaborators. Too much emphasis is placed on seeing if computers are as good as humans at a particular task. But I don't want to live in a world where computers are doing everything and taking all of our jobs and taking all the fun out of life. I want a computer to help me do the boring stuff so that I can focus on being creative and doing what I enjoy. And so just as all of machine learning and artificial intelligence is objective optimization, that's the objective that we should be trying to optimize, both for individual explanations and for the overall systems that they're a part of. This is just a single lecture from a course. YouTube likes to show you these videos out of order, but if you go to the course webpage linked below, you can see the lectures in the right order, and you can get resources like homeworks or suggested reading. You can also visit quanta.org if you want to learn about our systems for creating computers that can answer questions, where Quanta stands for question answering is not a trivial activity. If you want to help the channel, provide a big gradient to the algorithm by liking and subscribing.